Hi everyone, I'm Aditi and today I'll be presenting our work on proactive refresh for accountable threshold signatures. This is joint work with Boneh and Lior Rotem at Stanford University. Signatures are a way to digitally sign things like transactions or messages. They are used in many applications ranging from social networks to online banking and blockchains. The way signatures work is Alice would generate a public key PK, which she'll share with everyone, and a corresponding secret key SK, which she'll store on her personal device, let's say her laptop. Then she can use this secret key to sign any message M, for example, send $100 to Bob, and get a signature Sigma. Anyone can verify the signature by using Alice's public key PK and the message M. Since Sigma here was honestly generated by Alice, this will be a valid signature. Additionally, signatures are also unforgeable under the chosen message attack. The focus of today's talk is threshold signatures, which are used to distribute the secret key among multiple people. Let's say we have three parties, Alice, Bob, and Charlie, and a threshold of 2. We can first run keygen to get a public key PK and a secret key for each party. Then, if we want a signature on some message M, we can send it to any two parties, let's say Alice and Charlie. They would then respond with their signature shares sigma 1 and sigma 3, which can be combined to get a full signature sigma. The main benefit of threshold signatures is because no single party stores the whole secret key, an attacker will need to hack at least T parties to be able to forge signatures. More formally, a threshold signature has 4 algorithms: keygen, which returns the public key and the secret keys; a sign function, which returns the signature share for a party for some quorum J of size T; a combine algorithm that combines signature shares to get a full signature; and verify, which checks whether the sigma is a valid signature on M with respect to the public key PK. Somewhat informally, a secure threshold signature scheme has the following two properties. First, it's correct, meaning that combining honest signatures from any coalition of size T gives a valid signature. And secondly, they're unforgeable, which I'll precisely define later in the talk. Existing threshold schemes fall into two categories. The first are called private threshold signatures, wherein signatures are sampled from a distribution which is independent of the signing quorum. The second type is called accountable threshold signatures, where we can track who all signed based on the signature. Specifically, there is a trace function which takes as input the public key PK, the message M, and a valid signature sigma, and outputs the coalition J that is responsible for signing sigma. Informally, these signature schemes are accountable, meaning one malicious coalition of signers cannot frame another set. To get accustomed to the accountability definition, let's take a trivial example. If we have a private threshold scheme with functions keygen, sign, and so on, could we just make it accountable by signing both the message and the quorum, meaning that we set the sign function to sign M, J? The answer is no, because if an attacker has secret keys for a quorum J, meaning that they control this quorum, then they can blame any other honest set J prime by simply signing M, J prime. And since the original threshold scheme is not accountable, there is no way to detect this. Next, let's see a trivial accountable threshold scheme to get more intuition. In this trivial scheme, key pairs for all parties are sampled independently for some signature scheme. In our example here, Alice, Bob, and Charlie each have a public key secret key pair, which is independent. The overall public key of the scheme is going to be the list of all these public keys from PK1 to PK3. Then, the signature on a message M is simply a list of signatures from all the parties involved. For example, let's say Alice and Bob want to sign something. They will use their own secret keys to generate signatures sigma 1 and sigma 2, and the overall signature is simply the list sigma 1 and sigma 2. To verify such a signature, we verify sigma 1 with respect to PK1 and verify sigma 2 with respect to PK2. Similarly, a signature from Bob and Charlie is just a concatenation of sigma 2 and sigma 3. This scheme is very inefficient since, firstly, it has large signatures, which are of size at least T times lambda, where lambda is the security parameter. And these signatures are also slow to verify because we need to verify T individual signatures. Most real-world deployments today still use this trivial ATS construction, even though there exist more efficient ATS schemes which have short signatures and efficient verification. And in our talk today, we will give another reason why you should not use the trivial ATS, and to explain that reason, we will talk about perpetual leakage. In our setting with 3 parties with secret key shares, we know that the attacker needs to hack at least 2 parties. Let's say it takes the adversary roughly 1 week to hack into party 1. If they're really hardworking, they can hack 2 parties in 2 weeks, and now they have 2 secret key shares and they can use them to sign any message that they want. This problem is called perpetual leakage. To protect against such attacks, one solution is proactive refresh. Let's see what that means. So in the first week, the adversary will hack Alice and gets SK1. But at the end of week 1, Alice, Bob and Charlie run some fancy update protocol together and refresh their secret key shares to SK1 prime, SK2 prime and so on. These new keys are unrelated to the original secret keys except for they can still generate a valid signature with respect to the same public key PK. Now, when the adversary hacks into Bob's laptop in week 2, they will get SK2 prime. Since these secret keys are unrelated, the adversary cannot combine signatures from SK1 and SK2 prime, meaning the only way the adversary can forge signatures in this setup is if they hack 2 laptops within the same week. This property makes our signature scheme more secure informally. In the literature, there is a lot of existing work on private threshold signatures with proactive refresh and also accountable threshold signatures. Unfortunately, there is no prior work on accountable threshold signatures that support proactive refresh. This is because, at first glance, this might seem impossible. Secret keys are actually what are used to hold users accountable. But if we refresh the secret keys, how are we going to trace signatures back to their signers? What's worse is that the trivial ATS that we saw before is actually not refreshable at all. And here's why. Let's say that the adversary hacks into Alice's laptop in the first week and gets SK1. In week 2, we will update the secret key shares to SK1 prime, SK2 prime, and so on. Then the adversary would get SK2 prime when they hack Bob in the second week. But the sad part is that SK1 is still a valid secret key with respect to the public key PK1, which remains unchanged. Therefore, the adversary can still use SK1 to get sigma 1 and SK2 prime to get sigma 2 prime, and this will give them a valid signature. In fact, it is impossible to securely refresh secret keys without changing the public key in this trivial ATS scheme. What this means is that for applications that use this trivial ATS in the real world, the only way to protect against perpetual leakage is to generate a brand new public key and corresponding secret keys. For an example of a bank using signatures for transactions, if they want to refresh their keys, they will need to inform every one of their clients about the new public key. This is really cumbersome, because of which it can be really hard to refresh keys frequently. This brings us to our work where we define secure proactive refresh for an accountable threshold scheme. I'll cover this in the next few slides. We also present 5 constructions that are accountable and securely refreshable. The first one is a combinatorial ATS-PR scheme, which is strongly secure. I'll explain what that means in a little bit. But this is efficient only when n choose t is small. Next, we have a 2-level ATS-PR scheme, which is again strongly secure but has large signatures. Our third construction is an RSA-based instantiation of the 2-level scheme. This is strongly secure and has kind of short signatures. They are of size t plus poly lambda, but these are still longer than our last 2 constructions. The last 2 are BLS and Schnorr based. Both of them are very efficient. They have short signatures, but they do not achieve our strongest notion of security. In the follow-up work, we have constructed a 2-level pairing-based scheme that is strongly secure and also has constant size public keys, and you can find that on ePrint. We'll now start by defining the security notions for an accountable threshold scheme with proactive refresh. The first notion is unforgeability, meaning that the adversary should not be able to forge signatures. We define 2 levels of unforgeability called UF1, which is the stronger notion, and UF0. These are based on the work of Bellare et al. From 2022. The second notion is accountability, which basically means that a malicious set of signers cannot frame another set. We define 2 levels of accountability called ACC1, which is the stronger notion, and ACC0. Combining these together, we get a total of 4 notions of security, UFB and ACCB prime, where B and B prime can be 0 or 1. We use a game-based definition for all our security notions. And here's the setup for the game. We have the challenger on the left and the adversary on the right. The game starts with the adversary sending N, which is the number of parties, T, which is the threshold, and E, which is the number of epochs, to the challenger. The challenger then runs keygen to get the public key and secret keys for all parties. These secret keys correspond to the first epoch. The challenger then also runs the update protocol to generate the secret keys for epoch 2, epoch 3, and so on till epoch E. The challenger then sends the public key PK back to the adversary. Note here that the challenger can produce secret keys for all the epochs at setup time because we're assuming that all parties behave honestly during the update protocol. We discuss handling malicious updates in our paper, but we will not cover that today. After the setup, the adversary can query two oracles. The first is the secret key oracle, which models an attacker hacking into party I in week E. Here, the challenger will simply return the corresponding secret key, which is SKIE. The second oracle is the signing oracle, which models the attacker requesting signature shares in week E. The challenger simply responds with the corresponding signature. The adversary can call both these oracles polynomial number of times, and in the end, the adversary returns a forgery, which is the signature sigma star and a message m star. We say that the adversary wins the UF1 game, which is the stronger notion of unforgeability, if it produces a valid forgery on m star non-trivially. What we mean by that is in each epoch, the number of secret key oracle calls plus the number of signing calls on m star is less than t. Note that if in any single epoch, the adversary had gotten T signature shares or T secret keys, then making a valid signature would have been trivial. We say that the scheme is UF1 secure if no efficient adversary can win this game. To define UF0, which is the weaker notion of unforgeability, we use the same game as UF1 but with the following restrictions on the adversary. First, we consider the adversary to be semi-adaptive. What this means is that in each epoch, the adversary makes all the secret key oracle calls first before they can start calling the signing oracle. Intuitively, what this means is that in each epoch, the adversary has to first tell us which parties are going to be corrupt in this epoch. Also, this is semi-adaptive because the adversary can corrupt different parties in different epochs, but it cannot adaptively corrupt parties within one epoch. The second restriction on the adversary is that it cannot query signature shares on m star. This is actually the notion of unforgeability used in many other papers as well. And we say that an ATS scheme with proactive refresh is UF0 secure if no efficient adversary can win this game. Moving on to accountability, which intuitively means that a malicious set of signers cannot frame another set. We use the exact same game that we saw before with secret key and signing oracles, and the only thing that changes is the winning condition for the adversary. For ACC1, which is the stronger notion of accountability, we say that the adversary wins if sigma star is a valid signature on m star, and for every epoch E, there is some party IE such that the adversary does not query the secret key oracle for IE in this epoch, and it also does not query the signature oracle on IE for m star in this epoch. But IE shows up in the trace of signature sigma star. Intuitively, party IE was not involved in epoch E, but it has been falsely blamed to be involved. This does sound a little complicated, but this is indeed the right definition, and you can check out the paper to see why. Lastly, we say that the scheme is ACC1 secure if no efficient adversary can win this game. Next, for ACC0, which is the weaker notion of accountability, we again have the same game as ACC1, and the only thing that changes is the winning condition for the adversary. We say that the adversary wins if there is a single party I for which the adversary never queries the secret key in any epoch. Also, the adversary never asks this party to sign m star in any epoch, but this party shows up in the trace of signature sigma star. Intuitively, this party I was not involved in any epoch, but it has still been falsely blamed for signing sigma star. And we say that a scheme is ACC0 secure if no efficient adversary can win this game. Here's a more detailed overview of our constructions with precise security properties. The first three constructions, which are the combinatorial one, the two-level one, and the RSA-based, all satisfy UF1 and ACC1, which are our stronger notions of unforgeability and accountability. The BLS and Schnorr-based constructions only satisfy UF0 and ACC0, but they can achieve semi-adaptive UF1 with stronger assumptions. Today, we'll first start with the BLS-based scheme since it's the simplest and the most practical. Here's a quick overview of BLS signature scheme to refresh our memory. We have a group G of prime order Q and generator G. We have a bilinear pairing E that goes from G cross G to GT, which is also of order Q. And we have a hash function that goes from the message space M to the group G. In key generation, we sample a random number alpha and set that to be the secret key. And we set the public key pk to be G to the power alpha. To sign a message M, we hash the message and raise it to the power alpha. And to verify the signature, we check the pairing of G, sigma with the pairing of the public key with hash of M. Now, let's look at how a BLS-based ATS scheme works without proactive refresh. In key generation, all parties just randomly sample the secret keys. We then define a separate public key for each party, pki, which is going to be equal to G to the power ski. The overall public key is just a list of all public keys. We also define a separate public key for each subset J of size T, and this is defined as the product of pki's of all the signers in the set. This is basically equal to G raised to the power the sum of secret keys of all parties in J. Note that this is publicly computable from the list pk1 to pkn. Additionally, we are not considering row key attacks here. This is a simplified version with a DKG. In our paper, we discuss how a DKG can be avoided by letting parties generate their keys locally and modifying the scheme to protect against row key attacks. Signing in this ATS is the same as classic BLS. We hash the message and raise it to the power SKI. And to combine signature shares, we simply multiply them together and also return the set of signers. So the full signature sigma in this case is going to be hash of M raised to the power SKI plus SKJ. And we can see that this is indeed a valid signature with respect to the public key of the set I, j, which is G to the power SKI plus SKJ. The trace function of this ATS simply returns the set J included in the signature. Now, we want to add proactive refresh to this accountable threshold scheme. Let's see what happens if we simply use the standard proactive refresh here, which is T out of n Shamir sharing of 0, and if we add the Shamir shares deltas to the secret keys. So basically, sk1 prime will become sk1 plus delta 1 and so on. The public key is going to remain the same as before. Then, the new signature sigma prime in this refreshed model is going to be hash of M raised to the power the sum of new secret keys. This will simplify to hash of M raised to the power ski plus skj plus delta I plus delta j. But note that the public key is still the same with ski plus skj in the exponent. Hence, sigma prime is actually not a valid signature because delta I plus delta j is not 0. The main insight we use to solve this issue is that Shamir sharing of 0 has the following property that for any ij in 1, 2, 3, if we do Lagrange interpolation, we get 0, meaning lambda I times delta I plus lambda j times delta j is 0, where these lambdas are the Lagrange coefficients. Now, based on this insight, consider a modified scheme where the public key for the set J is the product of pki raised to the power lambda i's. This means that pkj is going to be equal to G to the power the sum of ski times lambda I for all I in the set J. We also modify the combine function to multiply sigma I raised to the power lambda I with sigma j raised to the power lambda j. What this means is that the signature sigma prime is now going to be hash of M raised to the power lambda I times ski prime plus lambda j times skj prime. This will simplify to lambda I times ski plus lambda j times skj plus 0 because the interpolation of deltas is going to be 0. Now let's compare this with the public key of the set I, j, which is G raised to the power the sum of lambda I times ski. As we can see, sigma prime is indeed a valid signature with respect to this public key. And that's it. This is our BLS-based scheme and we call this BLS-PR. Its correctness is trivial. Now we'll move on to the security properties. We have proved UF0 and ACC0 for our scheme by reducing it to the unforgeability of BLS. More formally, for every adversary A for the UF0 and ACC0 games respectively, there exist adversaries B1 and B2 for the unforgeability of BLS such that the advantage of A is less than n times the advantage of B1 and B2 respectively. Here n max is an upper bound on the number of signers. Unfortunately, our scheme cannot achieve ACC1. In our paper, we show an efficient adversary that breaks ACC1 for BLS-PR. Next, we'll look at our two-level ATS-PR scheme. This is a generic scheme and we use two building blocks for it. The first one is an n out of n threshold signature with proactive refresh. This scheme need not be accountable and we refer to it as sref. Second, we use a t out of n accountable threshold signature scheme. This one does not need to be refreshable and we refer to it as sac. Additionally, we use pi to refer to the DKG protocol for this accountable scheme. So the high-level idea of a two-level scheme is as follows. Let's say we have pkref and skref-i as the public key and the secret keys for the refreshable scheme sref. Similarly, we have pkac and skac-i as the keys for the accountable scheme sac. To sign a message M, first we use the refreshable scheme to sign the accountable scheme. What I mean by that is that we sign the public key of the accountable scheme, which is pkac, using the refreshable scheme. So we call sref.sign, sref.combine, and we'll get a full signature sigma pk. Next, we use the accountable scheme to sign the message M, meaning we call sac.sign, sac.combine, and this will give us a signature sigma M on the message M. The full signature then is going to be three things. The first is sigma pk, sigma M, and the third thing is pkac, which is the public key of the accountable scheme. Lastly, the public key of our overall scheme is just pkref, which is the public key of the refreshable scheme. Also note here that the signing protocols can be interactive or non-interactive depending on which schemes we use. Next, we'll see how to refresh the keys in our two-level scheme. The first thing we do is we simply refresh the secret keys of the refreshable scheme. So we'll call sref.update and we'll get new secret keys skref-i prime for the next epoch. Note that since we only refresh the keys, the public key pkref is going to remain the same. The second thing we do is for the accountable scheme, observe that it is not refreshable. So what we do instead is we simply run the DKG protocol pi to generate a brand new set of keys. So we'll get a new public key pkac prime and new secret keys skac-i prime for the new epoch. Lastly, we use the refreshable scheme to sign the new public key that we generated for the accountable scheme. So we'll call sref.sign, sref.combine to get a signature sigma pk prime on pkac prime. Finally, the new secret key for party I for the new epoch is going to include skac-i prime, which is the new secret key for the accountable scheme. It will have pkac prime, which is the new public key for the accountable scheme. It will also have skref-i prime, which is the secret key for the refreshable scheme. And lastly, sigma pk prime, which is the signature on pkac prime. More specifically, a signature on the message M in epoch E would look like this. It will have three things. The first is pkac E, which is the public key of the accountable scheme for this epoch. As we saw in the last slide, we have a new public key for the accountable scheme in each epoch, so we simply include the epoch-specific public key in the signature itself. The second thing is sigma pk, which is the signature on pkac E with respect to the refreshable scheme sref. The third thing is sigma M, which is the signature on the message M using the accountable scheme of this epoch. That covers our high-level overview of the two-level scheme. We'll now move on to the security analysis. We have proved that if the accountable scheme sac is unforgeable and accountable, and if the refreshable scheme sref is unforgeable, then this two-level scheme is unforgeable as well as accountable. More formally, for every b in 0 or 1, and for every adversary A which breaks UFB or ACC1 for our scheme, we have proved that there exist adversaries B1 and B2 such that the advantage of A is bounded by A times the advantage of B1 in breaking the accountable scheme plus the advantage of B2 in breaking the refreshable scheme sref. Here E is an upper bound on the number of epochs. Effectively, our scheme inherits the security properties from the underlying schemes. So for example, if both sac and sref achieve UF1 security, then our scheme will also achieve UF1 security. Next, let's see how efficient this two-level scheme is. In terms of the public key, it's simply the public key of the refreshable scheme sref. In terms of the signature size, we have a signature for the refreshable scheme, a signature for the accountable scheme, and a public key for the accountable scheme. Lastly, in terms of update complexity, we do a key refresh for sref, we do a signing for sref, and then we run the DKG protocol pi to get new keys for the accountable scheme. Now, there are many existing refreshable schemes which have a short public key, short signature, and also efficient key refresh and signing protocols. There are also a lot of accountable schemes known with short signatures. But what's missing is an accountable scheme that has a short public key and an efficient DKG protocol. No existing scheme has both these properties. So in our work, we also construct a new ATS scheme which has short public keys and an efficient DKG algorithm. This one is based on RSA accumulators. Additionally, in our follow-up work, which I also briefly mentioned before, we build a pairing-based ATS scheme with short public keys and an efficient DKG. To summarize, we give 5 constructions for an accountable threshold scheme with proactive refresh. The BLS construction that we saw today is the simplest and the most practical one. The Schnorr-based construction relies on similar ideas as the BLS one, but the analysis is much more complicated. The first 3 constructions achieve stronger notions of security but are not as efficient. Everyone is encouraged to look at our paper and its follow-up work to see the details. To conclude, most real-world systems today use the trivial ATS, which is bad because it has large signatures, it is slow to verify, and as we saw today, it's also not refreshable. This paper gives 5 constructions, including some that have short signatures, are fast to verify, and are also refreshable. Hence, we should not use the trivial ATS. Thank you.